Greetings students and welcome back to another video on tensors. In the previous video we left off by defining tensors using transformation laws, and we ended that video by discussing a couple of tensor operations like summation and scalar multiplication. In this video we're going to continue our discussion on tensor operations. We'll start by supposing we have two tensors S and T. The tensor S has a contravariant rank of P, so it has P indices in the superscript, and it has a covariant rank of Q, so it has Q indices in the subscript. On the other hand, the tensor T has a contravariant rank of R and a covariant rank of S. By the definition of the tensor we covered in the previous video, these are what the transformation laws for S and T look like. Note that the unbarred components are the tensor components in the unbarred coordinate system, and the barred components are the tensor components we get after doing a coordinate transformation to go to the barred coordinate system, xi bar. The first operation we'll cover in this video is the contraction. We're only going to need one tensor to discuss this operation because the contraction is a one tensor operation. Suppose S is a PQ tensor, like what we wrote above, the contravariant rank is P and the covariant rank is Q. In the unbarred coordinate system, its components look like this, what I've written here on the right-hand side. If I want to contract S with respect to a contravariant index IF and a covariant index JG, where F and G are any number from 1 to P and 1 to Q respectively, I replace each of those indices by the same index U. And now, since I have U as a repeated index, I conduct a summation over U from 1 to n to end up with my contracted matrix S prime. Now, some programming languages use this prime to mean transpose, but in this context it means contraction, not transpose. It might be difficult to understand what a contraction means from this definition, so let me illustrate the idea with an example on the side. Say I had a 2-2 tensor with contravariant indices I1 and I2 and covariant indices J1 and J2. The contraction of A relative to I2 and J1, for instance, would be found by replacing I2 and J1 by the same index U. And now, since the index U occurs twice, I can write the contraction of A as the sum of these individual elements, A super I1U sub UJ2. Assuming a 3D space where each index goes from 1 to 3, this is what I'll get. Basically the sum of three mixed tensors of rank 2, which would give me a 1-1 tensor in the end. Let's take a step back and look at what happened here. When I performed a contraction of A, the contravariant rank of A reduced by 1 because one of the contravariant indices turned into a dummy index that got summed over. In addition, the covariant rank of A also reduced by 1 because one of the covariant indices also turned into a dummy index that got summed over. So in general, the contraction S prime of S gives us a tensor with a contravariant rank reduced by 1 and a covariant rank reduced by 1. This is because one of the contravariant indices and one of the covariant indices gets summed over as a result of being replaced by the dummy index U. The proof of this statement is pretty simple. You just have to use the transformation law for S in the definition of contraction. I'm not actually going to prove this statement because although the proof is simple, the number of indices involved makes it a bit crazy to deal with, and the fact that the indices themselves have indices. But if you want a quick sketch of the proof, all you do is replace the contravariant index IF and the covariant index JG on the relevant barred quantities by the same letter U in the law of transformation. This, of course, follows the definition of the tensor contraction that I've written up here. After you do all the algebra and apply the reverse of the chain rule to reduce the sum of the product of partial derivatives into a single partial derivative of one independent variable with respect to another, which is actually just the Kronecker delta, after you do all this, you'll end up with the transformation law for a P-1, Q-1 tensor. Let's move on to the inner product. Say I've got my two tensors S and T with these transformation laws. If I want to take an inner product between S and T, I need to first pick a contravariant index on S, let's call that IF, and I need to pick a covariant index on T, let's call that LG. Of course, F can be any integer from 1 to P, and G can be any integer from 1 to S. What I do next is I equate those two chosen indices to a dummy index U, take the product of the components of S and T with that dummy index U in there, and then sum that product over U. When I do all this, I get the inner product of S and T with respect to the contravariant index IF and the covariant index LG. This inner product is a tensor with a total rank of P plus R plus Q plus S minus 2. Intuitively, this should make sense. By performing an inner product, we're effectively combining the tensors if you look at the right-hand side of the definition. So the resultant tensor should have a rank of P plus R plus Q plus S. Now the two get subtracted because two of the indices, one contravariant index and one covariant index, two of the indices go away because they get summed over. So this is why the total rank of an inner product tensor is P plus R plus Q plus S minus 2. I won't actually prove this fact because the proof is quite tedious, but it follows the same framework as the proof for contraction. Use the transformation laws for S and T, then apply the definition of the inner product. The transformation law you get at the end will represent a tensor of rank P plus R plus Q plus S minus 2. Now, although I'm not going to do a rigorous proof of the tensor character of the inner product, I will do an example of the inner product. We'll take the inner product of a contravariant vector V and a covariant vector U. The transformation law for V looks like this, and the transformation law for U looks like this. What we'll do is we'll equate the contravariant index on V and the covariant index on U to the same index K. Then we'll take the product of these two equations, and the result will give us our inner product. The product of these two partial derivatives can be shown to be the Kronecker delta function using the reverse chain rule I described earlier in the video. Once you have the Kronecker delta, you can use the fact that the Kronecker delta is only non-zero when the indices are equal to simplify this inner product to the following. And this makes sense. You've essentially got a scalar on the right-hand side that stays the exact same on coordinate transformation. That's made evident by the fact that there's no partial derivatives involving the coordinates here. So the inner product of a contravariant and covariant vector is a scalar, which does not vary when there's a change of coordinates. It is invariant. There's no coordinate partial derivatives in this transformation law. You might recall a theorem that I stated about invariance in a previous video, that the inner product of a contravariant and covariant vector is an invariant. I just proved this theorem right here. And because the inner product of a contravariant and covariant vector is a scalar, which is a tensor of rank 0, we can also say that this inner product agrees with the rank rule we established for inner products. The rank of an inner product of two tensors is the sum of their total ranks minus 2. In this example, we've got two vectors. Their total rank is 2, obviously. And then we're subtracting 2 to get 0, which is consistent with the fact that we got a scalar, a rank 0 tensor over here. The last operation we're going to discuss in this video is the outer product. Let's take our same two tensors S and T that we've been using throughout this video and their corresponding transformation laws. The definition of the outer product is pretty simple, although in terms of calculation effort, outer products can be difficult to calculate by hand. The outer product of S and T is a tensor whose components are the product of each component of S with each component of T. Similar to an inner product, an outer product effectively combines two tensors. The difference here is that I'm not summing over any index, so there's no indices that disappear when we calculate outer products. Therefore, the rank of an outer product is the sum of the ranks of the individual tensors S and T. In addition, the outer product has a contravariant rank of P plus R, the sum of the contravariant ranks of S and T, and a covariant rank of Q plus S, which is the sum of the covariant ranks of S and T. I invite you to prove this statement using the transformation laws of S and T and the definition of outer product. To illustrate what I mean by outer product, let's take the outer product of two vectors, a contravariant vector a1, a2, a3, and a covariant vector b1, b2, b3, which I've written as a row vector. What we do is multiply each component of A by each component of B and put that into a higher rank tensor. So we'll multiply all the A1s by the B1s, B2s, B3s, and repeat the process for the A2s and the A3s. What we get in the end is this mixed tensor of rank 2, which I've expressed here as a matrix. Remember, I've said this multiple times now, matrices are not tensors, they're merely used to express rank 2 tensors. Now just a note, I've used the term outer product here, but there's actually many names for the operation that functionally does the same thing to the components as the outer product. Some books use the term Kronecker product to refer to the outer product, and the Kronecker product is basically a way of combining matrices by multiplying each component of one matrix with each component of the other matrix, similar to what we do in an outer product. An outer product is also called a tensor product, which is how we used it here, to combine lower rank tensors to form a higher rank tensor. Even Wikipedia uses the term outer product in a slightly different context. It refers to the outer product only in the context of combining vectors to form matrices. Some books also call an outer product of tensors a direct product, which is typically used to combine two algebraic groups. I don't know, it's weird. So depending on where you go, textbooks and online sources use the term outer product in different contexts, and often interchangeably with one of these other terms I mentioned. So in order to prevent confusion, I'm going to use the term outer product to exclusively refer to the tensor product, i.e. an outer product of two tensors is a tensor whose rank is the sum of the ranks of those individual tensors. In this series, I'm going to use the outer product exclusively in the context of tensors. Anyway, that should do it for this lecture. I'd like to thank the following patrons for supporting me at the $5 level or higher. I've linked my Patreon account in the description for you to check out. And that's it. If you enjoyed the video, feel free to like and subscribe. This is the Faculty of Khan, signing out.